All right, let's dive into this explainer. You already know the baseline. Normal neutron stars. A massive star dies, and gravity crushes what's left to unimaginable densities. We're talking about the absolute densest things in the universe. Well, short of a black hole anyway. It's an environment so extreme, it pushes our understanding of quantum mechanics to the absolute limit, creating an object where the fundamental strong interaction is absolutely essential. But, it's just human nature to ask, what happens if we squeeze even harder? I mean, before gravity totally wins and rips a hole in space-time to form a black hole, is there some hidden phase of reality waiting to be unlocked right at the edge? And that brings us to the core of today's explainer, the cosmic detective story, hunting the Quark Star. We're going looking for the ultimate state of matter, hiding inside the most extreme objects out there. We're going to look at the theory, the microscopic physics, and the astronomical smoking guns of these hypothetical stars. Section 1. Beyond the neutron star, breaking the limits. Let's see what happens when the physics of a dead star are pushed completely past their breaking point. So, look at the profound contrast between these two types of stars. A classic neutron star is held together entirely by gravity, but a quark star? That's a completely different beast. It is a self-bound object. It's held together not just by gravity, but literally by the strong nuclear force itself. Instead of distinct protons and neutrons, a quark star is made up of the absolute fundamental building blocks of matter, free up, down, and, this is absolutely key, strange quarks. Which means we need to talk about strange quark matter, or SQM. See, if you just have up and down quarks floating around, it's highly unstable. But adding that strange quark into the mix, that changes the game. It theoretically stabilizes the whole system. It actually lowers the energy per baryon, creating this massive bulk quark phase that's electrically neutral and locked into a continuous, insanely dense state. Moving on to Section 2, unlocking the quark, the deconfinement transition. Let's zoom in from the star itself, down to the quantum level, and see how this strange matter is actually born. Okay, the magic word here is deconfinement. Usually, quarks are tightly locked up inside protons and neutrons, right? But when the sheer gravity and pressure inside a collapsing star hit a certain critical threshold, those individual neutrons literally melt together. The subatomic boundaries just dissolve. What you're left with is this continuous, sprawling sea of free interacting quarks. Researchers at RECON have a great analogy for this. They compare it to water changing phases. Think of neutrons boiling down into a uniform soup of quarks. It might be a super sharp, sudden phase transition like water hitting a rolling boil, or it could be more of a fuzzy, gradual shift. But either way, the fundamental building blocks of that star are completely transformed. And the stakes here are frankly mind-blowing. The Bodmer-Witten conjecture suggests that strange quark matter might actually have a lower energy per baryon than iron-56. Now, we normally think of iron-56 as the most stable element there is. If this conjecture holds up, strange matter, not the atoms that make up you, me, and the Earth, is the absolute true ground state of all matter in the universe. Which means we're essentially just living in a metastable state. Crazy, right? Section 3. Anatomy of a quark star. Inside the enigma. Now that we've got a handle on strange matter, let's dissect the theoretical anatomy of one of these things. When we compare the two, the standard neutron star is incredibly complex. You've got an outer crust of ions, an inner crust of superfluid neutrons, and these highly layered cores. But the quark star? Radically simple. It's basically a massive, uniform core of strange quark matter, maybe wrapped in a microscopic outer crust. It's essentially a single continuous drop of nuclear matter, just scaled up to the size of a city. And the surface of this thing is completely mind-bending. The quark surface itself is incredibly sharp. We're talking maybe 1 femtometer thick, literally the scale of the strong nuclear force. But the electrons, which are bound by Coulomb forces, actually bulge out hundreds of Fermis beyond that, forming this massive dipole layer. That layer can either suspend a thin, normal nuclear crust, or the star can just be bare. And here's a wild detail. If it is a bare quark star, matter falling onto it wouldn't hit an Eddington limit. That means it could blast out photon luminosities greater than 10 to the 30th ergs per second. Just unfathomable brightness. Because of that massive electron displacement, a bare quark star would also have an ultra-high electric surface field. We're talking 10 to the 18th to 10 to the 19th volts per centimeter. That energy density is so immense that it physically alters the mass and radius of the star. It completely dwarfs absolutely anything we see on a normal neutron star. Section 4. The masquerade problem. Hiding in plain sight. So, if these things are so extreme, why haven't we definitively spotted one yet? Well, that brings us to a huge astrophysical mystery. It all comes down to the masquerade problem. Basically, a quark star's mass and radius are incredibly similar to a regular neutron star, sometimes separated by just a few miles in diameter. So, from thousands of light years away, a quark star and a heavy neutron star look practically identical through our telescopes. They are perfectly masquerading as the mundane. Since they're so good at hiding, astrophysicists have to look for the specific triggers that could suddenly spark that conversion from a neutron star into a quark star. It takes a huge energy barrier to get there. Triggers could be the violent merger of two neutron stars, mass accreting from a companion star, or, and this is a really fun twist, potential interactions with hidden sectors of dark matter. The idea is that dark matter could inject deca-GeV energies straight into the star's core and literally spark the transition. Section 5. Hunting for strange matter, the smoking guns. Which brings us to the active cosmic detective work astronomers are doing right now. So if they look totally identical from afar, how do we actually crack the masquerade problem? How do we identify one? Well, we have to look for extreme, transient anomalies, things that traditional physics models just throw their hands up at. We're looking for highly specific deviations. For instance, rotation. A quark star can spin way faster than a neutron star without ripping itself to shreds, hitting sub-millisecond rotation periods right near the Kepler limit. We also look for unusually rapid cooling. And with gravitational wave astronomy, the density jump, or latent heat, during a phase transition on a star merger would cause a very characteristic sudden spike in the post-merger gravitational wave frequency. The exciting part is, we already have tantalizing candidates. Take the pulsar 3C58. It looks like a neutron star, but it's cooling off way, way faster than any standard model says it should. That rapid cooling could absolutely be driven by the intense neutrino emission you'd expect from a phase change right into strange quark matter. See, if a star hits that critical mass, the transition from hadrons to quarks is not a slow burn. The simulation data shows us it triggers incredibly specific, violent changes in the central baryon density, quark volume fraction, and temperature, all in literally a fraction of a second. When you look at the simulated models, you see these massive, sharp spikes in luminosity. This sudden deconfinement into quark matter would unleash a highly detectable burst of neutrinos. If our Earth-based observatories catch a spike that looks exactly like this, that's it. That is the definitive forensic signature of a quark star being born. It's an astronomical fingerprint, and we are just waiting to catch it. To wrap up this explainer, I'll leave you with this. Are some of the neutron stars we've been observing for decades actually giant cosmic drops of strange matter hiding in plain sight? Because if we finally catch a quark star in the act, it's not just another celestial body for the catalog. It proves the Bodmer-Witten conjecture. It fundamentally rewrites our understanding of particle physics, the strong force, and the true ground state of reality itself. So keep your eyes on the data.